SHARCNet provides a set of high-performance computing resources that are freely available to Canadian researchers and their international collaborators. These resources come in the form of compute hardware and storage, documentation, and technical support. The Getting Started with SHARCNet presentation is an efficient way of getting our newest users up and running as quickly as possible. This webinar will take the form of a slide presentation presenting the overview of the resources available at SHARCNet, and then a tour of the online documentation, including the portal and the wiki documents. And then we'll go over a demonstration of using SHARCNet systems at the command line. SHARCNet is a consortium of 18 Ontario institutions providing advanced computing resources and support. SHARCNet stands for the Shared Hierarchical Academic Research Computing Network, member of Compute Canada, and has more than 3,000 Canadian and international users. Several thousand CPU cores are available, many GPUs, and specialized network capacity. Getting help and the online resources are an important part of SHARCNet. The SHARCNet website provides extensive information about systems, software, and general help. In terms of general documentation, there's a user-editable wiki page found in the web portal menu at Help and Help Wiki. It contains a knowledge base, expanded frequently asked questions, as well as tutorials and detailed documentation on systems and software. And we'll go over a tour of this after these presentations. You can also find at the portal a system status. The system notice history, the present status, and statistics are available in the web portal through the facilities page. System notices are also sent via email and posted on RSS. And through these resources, you can sign up for web notices on specific systems or softwares that you're using. If you run into problems, and there are a lot of resources, and you want to find out specifics about how they run, you can search the web portal, and doing a problem search on the web portal will return relevant problem tickets, so you can see if these issues have been resolved in the past. Getting help at SHARCNet, and particularly through the problem ticket system, you can go to Help and Problems on the web portal, and this is the most efficient way to get help for use with these systems. We'll go over the path of this through the portal. Basically, this is where you can submit an issue to SHARCNet staff, and this will be sent through a triage, and the most appropriate support staff will be directed to assist you as quickly as possible. Of course, whenever you're filling out these support tickets, it's best to include as much information as possible. The ticket will be assigned based on whether it's related to a specific system or a specific software or even a specific research domain. So including all of that information in your ticket is valuable in terms of getting it assigned as quickly as possible. If your ticket has to do with specific jobs, then also include things like the job ID number that was assigned by the scheduler and the specific error messages that are being returned or lack of error messages, as well as how the job was submitted, giving information such as the software that was run, but also the specific submit function that was used to start the job. So some of the essentials in terms of the computing environment. There are several systems that are heterogeneous at SHARCNet. There are clusters, SMPs, we have GPU systems, as well as interactive visualization systems. The operating systems on these machines are typically Linux, mainly CentOS, but also HP XE and Fedora. We support several languages, all of which are documented in the software page in the portal. They include Fortran, C, C++, Java, as well as things like MATLAB and Python. Of course, because there's multiple cores in our systems and they're designed many times to operate in parallel, we support parallel development for MPI, POSIX threads, OpenMP, CUDA, and OpenACC. There are software modules installed, so you can select pre-built and configured software, as well as versions with the module command. In terms of the software, there's vast documentation to the portal page, as well as information about how you would actually use the modules for specific softwares and what versions are available to be loaded. There's also the batch scheduling, the SQ, the SHARCNet Unified Batch Execution Environment, which gives you access to the scheduler, and this is really how most of the production work is done on SHARCNet systems. And we can go over that once we get to the terminal demonstration. Essentials in terms of access to SHARCNet. So most SHARCNet systems are only accessible via Secure Shell, or SSH. We recommend authenticating using an SSH key agent, and you can see the SSH page in our help wiki for details. Using the authentication is mostly the most efficient way of accessing the system, but also the most secure. Of course, whenever you're using these systems, you want to be able to transfer files from your local machines or other remote servers onto the file systems that are accessible to the compute at SHARCNet. So in terms of file transfer programs, there's of course the Unix-based systems like SCP or SFTP and rsync. You can also use things like SSHFS for mounting the drives directly. If you're working from a Windows machine, you'll want a client, and we recommend things like MOBA Xterm for doing this. Essentials in terms of the file systems. On the SHARCNet systems, there are several file systems that have specific uses, and their intended use are really described by the quotas and access forms that they have. And I'll just go through three of the major systems, file systems here. The home system is where you end up whenever you first log into a system. So if you SSH onto any specific SHARCNet cluster, you'll end up in a home/your username directory. The file system has a quota, that is the amount of storage that's available for a user in that space. For the home file system, there's currently a 10 gig maximum. Now, in home, this is a hard limit, and that is if you put more than 10 gigs worth of data in this system, you'll begin to get write errors, as in there is no more space for you to write. So this will generate write errors at the time of exceeding that quota. Expiry is the amount of time that files are allowed to remain on the file system unchanged or updated. In home, there is no expiry. This is where you can leave files on a permanent basis. The access refers to where you can see the specific files from that specific file system. A unified access means that regardless of what system you log into, if you go to this file system, you'll see the same files. So if I log into home, my user, I put a data set in there, or actually more likely a program. If I then leave that system and then go log into another system, let's say Kraken, then that same file will be there. I will be looking at the exact same file system. So given this 10 gig quota, no expiry, and a unified access system, the purpose of home is really for source files and small configuration files. Another important property of the home system is that it is the system that is backed up. So although it is one of the smaller file systems that users have, it is backed up regularly and is a good place to keep source files and configuration files on long term in a secure place. The next file system is the work user space. The quota in work is bigger at 1 terabyte currently. It also has no expiry and is mostly unified. As you can see, the same system from all the clusters that you log into. The purpose of this system is for active data files. Also, it is auto-mounted, and it's a convenient system for doing work. The auto-mounted property can be important in that if you're using a client from a Windows machine to explore your file systems, you won't immediately see your work directory. That is, it's mounted once you try and access it to it. So if you're using a client to explore your file systems, you would actually have to type in work your username in order to see it. Another system is the Scratch. The Scratch has no quota in terms of the amount of storage on it, but rather has an expiry of 2 months. So this is to say that there is no limit in the size of data that you put on the system, but files that are unchanged for after 2 months are auto-deleted on the next Sunday. The access is also different for Scratch in that it's per cluster. So if you copy files into the Scratch file system on Orca, and then you log into Kraken, let's say, you will not see those same files. That is, the Scratch access is per cluster. The Scratch system is a good place for temporary files, checkpoints. You'll also find that there can be a performance increase in the Scratch file system for doing compute. Some useful storage-related commands are the quota. This lists usage across SHARCNet systems and will report if you're in the over quota status. du lists usage within directory. You should also note that there's, beyond the compute nodes that we have a data transfer node that is dtn.sharcnet.ca. This node is important as it's useful for transferring data. Now, it's different from the other systems in that it sees the internet in most SHARCNet file systems, and there's no CPU time limit on the system. So this is ideal for transferring large amounts of data in sort of one session. That process won't time out. As well, in many cases, you can actually transfer data between Scratch folders whose access are per cluster, but the DTN system can see both of them. Storage limits and enforcement. The Scratch file system have limited shared storage space. This is important to note. The Scratch system has no quota in terms of the storage space that a user can use, but at the end of the day, it's a physical space that if all users put all of their data on it, the space will fill up, and then we'll start to get errors. That as users are running jobs in the clusters, they'll run into write errors because the space is just full. So it's important to use the Scratch space as a temporary space, removing the data once the computation has happened. Users exceeding a quota or having over 1 million files in a work or Scratch will not be able to start new jobs. So this is another aspect of the file systems. Beyond the quotas and expiry, if you have too many small files on a system, it affects the performance of that system. So we've put a 1 million file cap on the number of files. If you go over the quota of any of these properties, what happens is that you'll be able to submit jobs, but they will not get into the run state until you clear up the over quota status. And you can do that by transferring files out of those directories and putting them in a more appropriate sort of longer term location. So some of the essentials in terms of the compute systems. We'll just go over a few of the systems. There are several more that you can find on the systems page of the portal. So Orca is one of our popular systems. It has many cores, over 8,000, and its target jobs are large MPI and threaded, typically under 24, and it has development nodes. Now, development nodes are a valuable resource in that you can log into these nodes and work interactively with the data with many of the same properties that the compute nodes that the scheduler has access to have. And this is a good place for sort of, prototyping and developing your work. SAW has over 2,000 cores and is good for medium to large MPI and threaded. It also has development nodes. There's Requin, or 1,500 cores, good for medium to large MPI. It also has a test queue. This is the only system that has a test queue. The test queue is used to submit jobs for a short period of time just to make sure that they will initiate and run based on the way that you're submitting them to the cluster. So Beyond a development node where you log in and use it interactively, what the test queue allows is for you to submit the job as you would to the scheduler, but it kind of jumps the queue and gets in before it typically would, being submitted normally to the scheduler. And then once it's in there, it can only run for an hour, but it'll give you a chance to see whether the job is starting properly, given the properties that you're handing over to the scheduler. Kraken is a large heterogeneous system with over 2,000 cores, which is typically used for serial farming and small to medium MPI threaded jobs. It also has 8 development nodes on it. And then there's the Monk system with over 400 cores and is one of the GPU systems. The systems at SHARCNet are diverse, and some of them are pretty heterogeneous. And what you'll want to do is decide which system is really best for the type of work that you're doing. And you can look at documentation on which system to use through the portal. There are also many other systems, contributed systems and specialty systems and visualization systems that you can explore through the portal. So whenever you're doing production work on SHARCNet systems, you'll want to know how to manage the jobs. Typical production work isn't done interactively on these systems, but rather jobs are defined and then submitted to the scheduler, and then they perform unsupervised on those systems. And you'll want to know how to interact with those jobs once they're running and completed. So all significant work is submitted to the system as a job. Jobs are run in batch mode by a job scheduling system, and it enforces policies to promote fair and efficient use. So you can imagine there are a lot of users submitting these jobs, and the scheduler is responsible for fitting these jobs in a timely manner and getting the most out of those compute resources based on the types of jobs that are being submitted. The way of interacting or submitting those jobs is using the sq sub command. And here's an example. From the command line, sq sub -r, you enter the runtime that you're expecting, -o. This is the log file that will contain the standard output of the program, or options. You specify the program and then the arguments for the program. So the required options are -r, a runtime estimate, and -o, the output file that will capture the standard output of the program that you're running. The runtime is the estimated runtime for the job. For example, R1D means that you're expecting this job to run for 1 day. There's a 7-day limit. After the runtime, the job is killed. So if you underestimate the amount of time the job is going to run and it reaches that time on the cluster, the scheduler will terminate that job. For parallel jobs, one has to specify the queue, either -q MPI or -q threaded or -q GPU, and the number of CPUs that are going to be used for the parallel job, in this case -n. Once jobs are submitted, you can check on the status of submitted jobs using sqjobs while logged into the system. If for any reason you need to stop or dequeue a running or queued job, you can use sqkill followed by the job ID number. There are certification limits and development options. Your user certification level determines the job size and runtime limits that you have. So users with a brand new account prior to completing the user quiz have level 0. This gives you access to 8 CPUs in 24 hours. Typically, people attending the New User Seminar or watching it now have this certification level. Once you complete the quiz, you have access to 256 CPUs at one time, as well as a 1-week limit runtime. And this is the certification level that you have after you've written the quiz. If you do need resources beyond this limit, you can contact us to see what options are available. For example, the RAC, Research Allocation Competition. Typically, resources beyond this are not necessary, and there are other options for finding it out, but this is handled on a case-by-case basis. There are multiple ways to develop work at SHARCNet. Of course, as we mentioned earlier, there's the cluster login nodes. Whenever you first log into a system, you go to the login node. This is a place where you can do small tasks. For example, data transfers, file handling. You can run small programs in here, as well as doing things like compiling programs and exploration. There are test queues where you can actually submit jobs to the queue, but avoid the typical queue wait time to see if the jobs will initiate properly. And this is only available on Requin at this point, which gives you a preemptive 1 job per user with a 1 hour maximum runtime. There are also cluster development nodes available on Kraken, Saw, Orca, and Monk, and you can access these by using the -y to allow you to work interactively on the system. So you log into the system, and then you log into a development node, and you can find the names of these through the systems page of the portal. Beyond the development nodes, there are also visualization workstations that give more access to graphical and interactive use. These systems basically allow you to log into a desktop with different operating systems that are on the same and have access to the same file systems that the compute resources have. So if there are computations that are running, that there are visualizations you want to run on, but you don't want to have to transfer the data back and forth to your local machine, you can actually log into these remote desktops and then access your data from there and perform visualization tasks. Some common mistakes to avoid whenever using SHARCNet systems. Do not run significant programs on the login nodes or directly on compute nodes. Whenever you're doing the prediction work on these systems, typically the process is to submit them as jobs or use the development nodes. Development nodes are intended for development purposes, running jobs, testing them, profiling them, editing procedures, but a fair amount of work can be done on those. Do not specify a maximum job runtime of 7 days or more memory than required for your program. So we recommend to pick an appropriate value, for example, 150% of the measured or expected runtime or memory per processor. Now, the scheduler uses these estimates to allocate the resources of all the jobs that are being submitted by all the users. If there are large overestimates of the time or the memory requirements of a job, this can lead to more idle cores and more wasted resources. These estimates really contribute to the efficiency of the system overall. So we highly recommend understanding the sort of timing that's required by your jobs, as well as the amount of memory, and then trying to give accurate estimates, allowing about 150%. Of course, you don't want to specify too short or too small a memory, as this will cause your jobs to terminate prematurely. Do not run unoptimized code. So, of course, we want all of the programs on our systems to be running as efficiently as possible. The efficiency of the entire system is dependent on the efficiency of all the programs running on it. So we highly recommend profiling and testing the efficiency and understanding how the program will scale up. We have information on how to do this, and our staff will provide support for helping in this way. Do not create millions of tiny files or large amounts of uncompressed, for example, ASCII output. Instead of generating many files or unoptimized files, you can aggregate files with tar or dar, or use binary or compressed file formats. And this will reduce the number of files as well as the size of data on the clusters and file systems. Of course, if you have any questions or concerns, an easy way to contact us is through help@sharcnet.ca. This is the same as submitting a help ticket through the portal, and we're making a recording of this available, of course. Now for a tour of the web resources at www.sharcnet.ca, where you'll get to a login page where you can either register or sign in as your user. Once you sign in as a user, you'll be really directed to your usage or activity page. Here you can find information about your jobs that have been running and a recent history of it. As a brand new user who hasn't completed the certification quiz, you can find the certification quiz at the top of the menu up in the upper left-hand corner. Once you complete this quiz successfully, you'll be up to level 1, and the resources that you have access to will be increased. You can manage your account in My Account and Settings, Details. You can change your password, etc., as well as access files, the policy files. You want to be familiar with all of these, for example, the acceptable use policy document, the scheduling policy, etc. There are plenty of resources for monitoring how the systems are running from within the portal, as well as access to documentation about the systems and software. In Facilities, you can go to Performance and check on the current performance, and you can see an overview of the systems and how much work is currently running on them. You can also get rundowns of information of the number of jobs, as well as some estimates of the wait times and systems for specific types of jobs. In Facilities and Systems, you can see a rundown of all of the systems that are available, the core systems, and by clicking on these, you can go to its documentation, where you get an overview of how the nodes are organized, as well as the resources that are available on them. You also get the software available for those systems, and by clicking on any one of these, you can go to that software's documentation. Importantly, you can also find the recent system notices on this page. These system notices also go out to the email lists to those users who are signed up for that list for this system. At the bottom of this page, you can find the visualization systems. From here, you can actually log in directly to one of these systems to start a visualization system. For example, if I click here, it'll bring me here, and I can sign into this system and start using it. The software page lists all of the software that is maintained and supported on our systems by our staff, applications, commercial compilers, etc. Beyond the software that is supported and maintained by our staff on our systems, it's also possible to install your own software within your user environment on the systems. When staff helps users install the system, these softwares within their environment on the systems, we document that software here on this page, and you can find information here about how those softwares are installed on the system, going here and finding instructions for that installation within the user space. Of course, the news and events, you can go to the calendar to find events that are coming up that are organized by SHARCNet. In particular, you can notice every 2 weeks we have a general interest seminar that's put on by our staff that talks for an hour about specific issues on high-performance computing and research computing. Within the help item, there's the FAQ knowledge base. This is a lot of information from getting started to tackling specific tasks on the system. A lot of this is made up by the interactions that we have with the ticket system. There's also the Help Wiki. In the Help Wiki, There's information about getting started, some hardware, programming help, visualization, as well as a list of online seminars. Here you can find all kinds of recordings of seminars that have been put on and recorded. Within the Help menu under Problems, you can click on the Submit button, and this will bring you to the ticket submission interface. Entering information here and a description of the issue, and then submitting it will go directly to our support staff, and then we try and resolve this and get back to the user within the day. Then in the About Us, in the Contacts and Directory, if you want to find support from a specific support staff, you can find our listings here, as well as some of our specializations. For the demonstration of using SHARCNet through the terminal, I'm going to do some common tasks. For example, transferring files from my local computer to the remote file systems at SHARCNet, and then looking at some source files in a text editor, compiling them and running them in the login node, and then actually submitting these jobs to the scheduler. Then once we go over those tasks, we'll actually look at loading software modules and using some software on the systems interactively on development nodes before then submitting those tasks as jobs to the scheduler with specific modules loaded. So to get started, I'll just use my notes here. I'm on my local computer, and I know that I have some demo files in a folder here. So what I'm going to do is I'm just going to go in here and take a look. I have this SNNU demo folder that I want to transfer over to the cluster in a demo folder that I have there. So what I'll do is I'll use the Linux SCP. So I'm going to secure copy the folder SNNU demo through the data transfer node at SHARCNet into my home directory in a demo folder. I'll just hit enter, and it will ask me for my authentication. And once I do that once with the SSH key, I should just be able to do everything without entering the password. So now we see that this is transferred over, and what I'm going to do is I'm going to go over to a cluster and then have a look at those files, compile it, and then run it in the login node. So the system I'm going to use is Kraken, so I will just SSH over to Kraken, SSH jdesjardins@kraken.sharcnet.ca, and this puts me in the login node at Kraken, and my current directory is my home directory. Now what I want to do is I want to go over to the folder that I just transferred over. So cd to demo and SNNU demo. And then list this, and I see that in here there's a snhw.c, the SHARCNet Hello World C program. So what I can do here in the login node, we don't want to do any big production work. We don't want to do any computation here. But there's probably a lot of people actually logged into this node, and what we can do is things like submit jobs. We can arrange and copy files, but we can also open text editors and take a look at some of our source files. So I'll just use Nano in this case, an intuitive text editor. Here we see this is just a basic print hello world program. So I'll just get it here. And then what I can do here in the login node is I can compile this program and then save it to SNHW. And we'll just list again. And we see here now that we have this executable SNHW. And then what I can do here is, because this is a very simple program, I'll just actually run it here in the login node at Kraken. And we say what it returns to the standard output is hello world, of course. Now, if this were an actual production job, what we would like to do is not run everything here in the login node, but actually submit it to the scheduler for it to run on the compute nodes. And the way that we do that is running the same program, but submitting it using SQ sub. So here I'm saying SQ sub with a runtime estimate of 5 minutes and specifying the -o output as snhw.out. And then this is the thing that's actually going to run. So if I submit this, I get a little warning here that we didn't specify the memory requirements, so it's assuming the 2 gig default. And then we say here that it was submitted as job ID, the value. Once the jobs are submitted to the schedule, we can take a look at what's happening using SQ jobs. So any current jobs or previous jobs that I had submitted will be listed in here. And just looking through it here. And here we see. So earlier today I ran some other jobs, and then this one that we just submitted now, ending in 578, is listed here at the bottom, and it's done. It was run CPU. It ended 15 seconds ago. So now in this directory, if I list again, I see that the output file was generated from the SQ sub command. And this output file just collects the standard output of the program that was run. So then if I take a look at this one using nano SN out, we see here that the output holds the standard output that we saw in the terminal whenever we just ran it at the login node, as well as a SHARCNet job epilogue that contains information about the resources that were actually used during the run of that procedure. This is important information for getting estimates of what to specify in terms of runtime and memory requirements of jobs in the future. Now let's say I find some more code that I like online. We'll just try and run a little MPI job here. I'll just copy this, and then I'll go back to the terminal, and I'll make a new file. So this time we'll call it nano SHARCNet hello world MPI. See? And then I'll paste that text that I found, and then I will save it. This ls. So here we see the new file, which is basically an MPI version of the hello world. What I can do is now I can compile this for MPI. I see this new executable MPI, and now instead of submitting it as a serial job, which will just do the single process, I'm going to submit it to the MPI queue using 4 cores. So let's copy this, paste it over here, and then submit that. Again, we get the warning that we didn't specify a memory estimate, so it's assuming the 2 gig default, and then we get the job ID returned here. Check my SQ jobs. And let's see how this does. So now we see that the job we just submitted is MPI. The MPI queue is done. It used 4 CPUs, the nodes that it ran on, and it finished 5 seconds ago. If I list the files that are in this directory now, we see that there's the snhw mpi.out. What I can do is I can take a look at that one. Out. And here we see here the standard output is basically the hello world from each of the 4 processes that we requested, as well as the SHARCNet job epilogue. So these are some of the common tasks we've already gone over. The transferring of data from the local computer over to the remote file space at SHARCNet, going to the login node, navigating over to the data we transferred, taking a look at source file in a text editor, compiling it, running it just locally in the login node, and then submitting the job to the scheduler, running it, and then looking at the output, where the standard output of the executables was collected, and then doing the same thing, compiling an MPI job and then running it. Now, another thing that we often want to do is be able to work with software that's available on SHARCNet interactively before we start submitting jobs. And one of the things to go over here is the use of modules. So what I'm going to do is I'm going to give an example of using software on SHARCNet, Octave, which is highly compatible with MATLAB and is good for profiling software and working interactively with data. But we can also run jobs through the scheduler in Octave. So what I'm going to do first is I'm just going to grab my notes. Now, we can log in with forwarding, so I'm going to log right out of the system. And then what I'm going to do is I'm going to log back in, just in case we want to take a look at figures while we're using Octave. We'll just add this -y option here. So this will bring me to Kraken again. And then once I'm in the login node at Kraken, what I'm going to do is I'm then going to SSH to a specific development node. In this case, we'll go to development node 5. Once I'm in here, I can check how many resources are free in terms of memory, and then we can also check what's currently running. And we can see that there are some other people using this, but there's plenty of memory left for us. And then we can also just keep track of our own work here. So what I'm going to do now is I'm going to go over to a folder where I know that I have some data. And from here, what I'm going to want to do is load some of these files in Octave once I have Octave running here in the development node. So really what I would like to do is at this point just start using the development node as though it was my local computer and work interactively with Octave. Now, if locally what I would do is I would just type Octave, and then this would be an Octave prompt. But here we see that it's not found. Now that's just because it's a module, and this module isn't loaded yet. So I can check the modules, module list, and we see here that Octave is not one of the modules loaded. So really what I would like to do is module load Octave, and there's a specific version that I want. So I would do something like this, and then we get this error back saying it's not compatible with Intel. So then just module unload Intel, and then try loading Octave again, and then here we have it, module list, and we see that we have Octave, and then we can just type Octave again. So now that the module was loaded and everything seems to be set up with the modules, I can start Octave here in the development node, and I can have now an Octave prompt, and I can just use it interactively as though I were on my local computer. And then some of the things that I can do is load some data files that I have in this directory. Load those, and while this is loading, we could open a new terminal, and then at Kraken SHARCNet.ca, and then I'll go to that same development node, Kraken Devel 5, and then I can just list my processes here so that we can watch the memory being used while this is running interactively. So I loaded some data from an EEG file, and I'm just going to run this correlation analysis, let's say. So this is something typically that I would like to do on large data sets. and across several data sets simultaneously. And what I'm just going to do is see how it runs here in the development nodes. And then we can basically watch the memory as it grows while Octave is running here in the development node. Let's get an idea of the timing. And although this won't run exactly like it runs in the compute nodes that are accessed by the scheduler, we can get some ideas of how things work. First of all, making sure that the code that I'm running is actually compatible with the modules that I'm using. So that's run nicely. And now what I want to do is actually, now that I've logged in, I've used Octave interactively to see if this procedure is working on the system. I'm going to log out of the development node and then actually execute this procedure by handing it over to the scheduler. So what I'm going to do is I'm going to log out. I'm going to quit Octave first, and then I'm going to log out of the development node. So here I am back in the login node of Kraken, and where am I? And what I want to do is then go back to the directory with my data. And then one of these M files is actually a function representing the procedure that I just ran. So let's just take a look at that quick. Right. So this is a script that loads the files that we just loaded and then runs the analysis and saves the output, exactly like what we just did. So what we would like to do now is just hand this script over to the scheduler, asking Octave to execute it. And the way that I do that is, now that I'm in the login node and I want to submit a Octave job, make sure that I check the modules, and we see now that I've left the development node, I'm back to the default modules. So I have to prepare my modules to make sure that the job will run. Module unload Intel. Load Octave, a specific version that I want. Module list. So these are the ones that are loaded, and then if I want to check which ones were available, I'll do module avail. And this is where I would see the Octave versions that. Right, 3.8.1, but not the latest 4, which was recently installed. Okay, so now I'm in my directory. I know that this is the specific M file that will run the procedure that I've tested inside the development node. So now what I want to do is I want to submit the job. In this vernacular, I'm going to do sq sub, estimating a runtime of 4 minutes, where my output file is going to be oct.out. And then the memory per process is 4 gigs, an estimate based on what I saw where it went over 2 gigs in the development node. And then I'm asking Octave to run to evaluate with the traditional flags, which favors MATLAB compatibility, the M file that I have here. So this job got submitted with this job ID, and then I can check SQ jobs to see where it's at. So now the terminal demonstration has gone over things beyond just transferring data and compiling, running in the login node, and submitting serial MPI jobs and looking at the output, but also taking care of modules and then executing scripts in software that was specified. And here we can see that the job is done. ls, and then oct.out, which would contain the standard output as well as the actual data file output of that job. And that's the demonstration of using SHARCNet from the terminal.